Hello everyone, my name is Elizabeth Mahood. I'm a third-year graduate student at Cornell University in the plant biology section, and my poster is entitled A Machine Learning Paradigm for Classifying Lipids and Other Metabolites into Major Structural Categories. I will say that I won't have time to address all the details in this poster, so if you have any questions, please email me at ehm79@cornell.edu. So this research was spurred by the current state of metabolomic studies, especially in plant systems, where metabolite identification is widely regarded as the bottleneck in current LCMS studies, because we can detect maybe up to thousands of metabolites now, but we cannot identify them, especially with the current systems that are in place. So machine learning, which I'll abbreviate as ML, and these algorithms have been used to predict metabolite structure from LCMS and MS peaks. An example of that is CSI finger ID, but these are currently limited to relatively small metabolites and they may yield false positives. So in light of this poster is going to cover proof of concept studies where we explored classification of metabolites into major chemical classes instead of trying to predict their exact structure. And so we did this by using machine learning with features derived from molecular formula and MS/MS fragmentation patterns. So the first application that we did was we took the lipids in the lipid blast database and classified them into their subclasses using supervised machine learning. So we made 3 types of models, all random forest models. One of them used only the formula for classification, one used only fragmentation patterns, and one used both. So all of the models did very well, and the MS/MS plus formula model did the best overall. The next step is we applied these models to new data that was experimentally derived rather than in silico derived, which is what Lipid Blast has done. So all of the fragmentation patterns in Lipid Blast were in silico generated. So we found a set of 146 lipid standards from Lipid Data Analyzer, and we benchmarked our model with them, and we benchmarked our model against a Lipid Blast and against something called naive formula lookup. And so what that is we took a formula from one of these Lipid Data Analyzer standards and asked if the formula was present in the Lipid Blast database. If it was present only once, we called that correct. And if it was present more than once, i.e. if the formula, if there were multiple lipids in different classes in Lipid Blast that had that same formula, we called that ambiguous. And if there were no lipids in the Lipid Blast database with that formula, we called that not predicted. And so we wanted to see how many lipids of the Lipid Data Analyzer standards our model got correct compared to Lipid Blast and naive formula lookup. And as you can see, our model did quite well in comparison with these benchmarks. So then we moved on to a broader set of metabolites, applying this model to a broad set of metabolites rather than just lipids. So we did 2 things here. First, on the left, we downloaded the MS/MS fragmentation patterns of flavonoids from the Respect for Phytochemicals database. What we're showing you here is that area under the receiver operating characteristic, and this score is 0.98, which is quite high. And we also downloaded formulas for different classes of metabolites within plant psych, and these classes, all of the classes within plant psych containing more than 50 instances were used, and figure B here denotes the AURC scores for classification of those metabolites, and again those are quite high. And so since we saw high AURCs across all classes, that reinforces the power of this method. And the next application that we did was looking at if our model could differentiate between structurally similar metabolites. So we generated in-house data for this, where we looked at fragmentation patterns for resin glycosides as well as acyl sugars. And so figure A there shows 2 exemplary resin glycoside and acyl sugar. And so we use the fragmentation patterns for these metabolites to see if our model could differentiate between them. And so in figure B, we can see that no resin glycosides were misclassified as acyl sugars, and the same can be said for acyl sugars. 99.8% of resin glycosides were classified correctly, and 53% of acyl sugars were classified correctly. That low number is probably because we had so few acyl sugars in comparison with resin glycosides. So we can see that yes, our model can differentiate between two structurally similar classes. We also wanted to see if our model could recognize characteristic fragments of these classes. So in figure C, we see 143, which is a C8 acyl chain, and this is a characteristic fragment of acyl sugars. And on the right, we see 3 different characteristic fragments of resin glycosides. And so we calculated the importance of these fragments in comparison with all of the other fragments and found that they were indeed, our model recognized them as being very important for determining if a metabolite is a resin glycoside or an acyl sugar. And so finally, we expanded this to the multi-label ChemOn ontology. A multi-label just means one metabolite may have several labels. And so we downloaded the formulas from all metabolites that were classified with ChemOnt in the ChemI database, and did classification for these different classes. And we found that the classes that had high numbers of metabolites did quite well, whereas classes with low metabolites did relatively poorly. And reasons for this are in conclusions. Thank you.